You can collect a sample, but you have to do it from a helicopter, so you have to be quick. It took about 5 minutes between points, so that you couldn't stop the rotor every time, because it would take too much time to start up again. So we were 2 people. We had to run out of the helicopter, pick a sample, come back while the rotor was running. You had 2 to 3 minutes or something like that.
Welcome to Polar Podcasts, where you'll hear stories from geologists who've spent their careers, their lives, exploring and studying the remarkable and remote geology of Greenland. Why did they become fascinated with Greenland? What were the problems and the discoveries that drove them? And what was it like working in these remote places where few people venture, even now? I'm Julie Hollis. In this episode, we hear more from Agnete Steenfelt, Emeritus Senior Scientist at the Geological Survey of Denmark and Greenland, about introducing a program of stream sediment sampling to surveys in East Greenland in the mid-1970s, a program that would ultimately grow to decades of work and tens of thousands of samples, covering almost the entirety of Greenland.
Having flown the area over 2 summers, we still had 3 summers of fieldwork in East Greenland where we could go back to the areas we found interesting, where we had increased gamma activity.
That is, increased gamma radiation detected from the aerial surveys.
And find out where they came from, or which rock types or which rock associations that produce these increased radiation. And so we used helicopters to go back to the areas. Also, when we had found an interesting area, we would eventually have a field camp there and track with our hand-borne instruments. We would be tracking, going forth and back over an area and measuring the variations to locate where the most intensive spot was. And then we could dig at this place and find out could we identify the radioactive material. And in many cases we could. We took samples, and then of course the next step was to bring them back to the laboratory and study the mineralogy and find out what kind of uraniferous mineral it could be, and from then on decide whether it was economic potential or not. So that was a very good learning process. But I also, while doing this work, I was thinking of another way of getting an overview of the area, and I'd always been interested in geochemistry, so I thought we should, in fact, make a geochemical survey over this area where we'd been flying. I mean, in our flights we register radiation from uranium, thorium and potassium, but in a geochemical survey you can actually get the response from uranium and be sure that when you're analyzing a rock for uranium, then it is uranium,
rather than potassium or thorium, which also emit gamma radiation.
So I was also inspired by Scandinavian colleagues, because in Scandinavia and also in Russia in those days, when geochemical laboratories made a lot of progress in analytical methods, that you could actually collect systematically over an area samples, soil or what was deposited at the bottom of streams, and then analyze it, and then you could see the variation in the contents of not only uranium, but in all the elements that the analytical methods would provide, which meant that then you could study the relation between high uranium and high contents of other metals. And thereby you could find out a probable association, whether uranium was part of a mineralizing system, also with copper and zinc or lead, or whether uranium was associated with the granite, with a high silicium or high potassium or high rare earth elements. In the beginning you couldn't analyze for rare earth elements, but that came in the 80s, 90s, and I started being able to do that. I mean, the principle in geochemical exploration is that when a rock weathers and is eroded by rainwater and streams, this material is taken in the stream sediment and is deposited somewhere along the course of the stream. And then you take a sample, and if you follow a stream, if you have some high values, you can take more samples upstream, and eventually you can get to the spot where your anomaly, the unusually high content, where it comes from. So it's very simple. Anyway, in East Greenland, we started up collecting material deposited at the bottom of streams, small streams. And we did this systematically And we could do that because we had sufficient amount of helicopter hours to do this. And so during 1976 and 1977, we covered a smaller area within our large survey area. And that was a very good experience. I mean, geochemical exploration hadn't been used a lot in Greenland before. There were a few local attempts close to the Messersvik lead zinc mine that was operated in the 50s. And so there were some people from Aachen who had done geochemical exploration in the Ardennes. They were invited to Greenland to do some small, what we called orientation surveys, where they would collect along a stream and look upon dispersal of various components along this stream by analyzing samples collected. With pretty good results. Then, I decided, because I was in charge of that. So I decided we should do that on a regional scale. So I looked at the drainage pattern, which was favorable to this type of exploration, and chose sampling points at as regular as possible intervals where we should land and pick a sample of what was deposited in the stream. And we did that. We had 2 or 3 sampling teams. And then we would also measure with our handheld scintillometer the radiation at the spots so that we could connect later the relation between the gamma activity and the actual uranium content in the stream. And we were also able to analyze for more elements, which was good because then we were gradually turning uranium exploration into the same methods for looking for other minerals. And in those days, the first and foremost were base metals. That means nickel, copper, zinc, lead. And that was exciting because you had to find out how do we do this in practice. I mean, you can collect a sample, but you have to do it from a helicopter. So you have to land and you have to be quick. It took about 5 minutes between points so that you couldn't stop the rotor every time because it would take too much time to just start up again. So we were 2 people. We had to run out of the helicopter and pick a sample, come back while the rotor was running, fast as possible. You had 2 to 3 minutes or something like that. Sometimes the helicopter had to land on top of a ravine and then you had to slide down to the stream, pick your sample and climb up again as fast as possible and then rush back into the machine. And then you have a paper bag of about 1/2 kilo of the sediment. And it was paper bags because it should be allowed to dry afterwards without taking the sample out of the bag. It's not to contaminate it with anything else. So what do you do with all these wet sample bags in a helicopter? So we had to create a system where you could put them in a box with holes in the bottom. They could stand there and then the water could drip through into another box that you had to remember to empty now and then. And we worked out the schedule where you could do this and then have a full stop, as we called it, where the pilot would stop the engine and we were allowed to rest for a coffee break or a lunch break or whatever. Or sometimes I asked for a full stop because I wanted to look at the rocks at this particular site. I found something interesting. When we were landing on a site, we would sit with the aerial photo, or a bunch of aerial photos, because we would shift from one aerial photo to the next while flying, and you had to keep track where you were. I would have a needle on my jacket. I would take the needle and make a hole where we were taking the sample, and then write on the backside of the aerial photo the number of the sample. So that's how we did, and that's how the mapping geologists did. They had a needle and they made a hole and wrote the locality number on the back. In those days, where everything you recorded was on some kind of paper, you really had to take good care of this. This was your field notes in a small book, your field maps, and your aerial photos. Yes, and we had aerial photos and maps in some particular sort of hardboard thing we could carry. And it was very easy to leave it on the helicopter float, because when you had to pick up your hammer or your rucksack or something else, or your sample and store it into the passenger compartment in the helicopter, whoops, it took off and my maps! And then we were in contact with a chemist who was in charge of some of the analysis, and he suggested that we should look for uranium in water. And he had figured out a method whereby you could analyze uranium in water. But because the content of uranium and other metals that you would like to look for is very, very small content, and so you had to concentrate it from 1 liter of water. So you had to fill your sample in 1 liter bottles, and you can imagine, they weigh about 1 kilo each. That was not really practical. But we did that on one summer, not over the entire area, but we had some test areas where we collected these 1 liter water bottles. And then we also had a year where we tried to store them in plastic bags. We tied a knot on a plastic bag with 1 liter of water in them, and they had to be sent back to Denmark in wooden boxes, and stacking plastic bags with water samples ends in losing water because of the pressure of the overlying bags and the squeeze water through even the tightest knot you can tie. Also because it's cold in Greenland, and you cannot tie a knot so tight when it's cold. Well, I mean, this is something that you experience when you're working with new techniques in an area. Well, in the end, the analytical procedure had improved so much that we could analyze just 100 milliliters, also for other elements. So we turned to this geochemical sampling that we continued to do over other areas in Greenland. We could then use 100 milliliter bottles, which of course helped a lot. That was the start of this, and we got promising results, and I was studying this, and we found out that the method worked. At first, where we had tried it out, where we knew there was some uranium in the rocks, and that worked well. And also on a regional scale, we could see that the uranium and other elements in the stream sediments corresponded nicely to what you could expect from the rocks that the stream was draining. And we also checked seasonal variations in the metal contents. We went back to a specific site and collected a sample each week. And then throughout the season, we had 2 months field seasons in those days. We could see how the metal content varied according to the flow of water. In the beginning, there's very little flow because most of the water is tied up in ice and snow. And then the melting season starts and you get more water, and so more material transported from further away, and we could follow this in the samples we collected. So there were many good experiences from working with this method. And then when we had learned enough and used the results in East Greenland, I was in charge of doing this over the rest of Greenland.
I'm Julie Hollis, and you've been listening to Polar Podcasts. In the next episode, we hear more from Emeritus Professor Kent Brooks about close encounters with polar bears while on geological fieldwork in East Greenland.